Hi, and welcome to the second part of the shrinking town problem. We're going to look at part B. If the population decay were always the same exponential rate, when did Pittsfield have that population of 175,000 people? Now, if you recall in the last version of it, in my function I moved my decimal over 4 places, basically dividing this by 10,000. So I'm going to have to make this 17.5 if I'm going to continue playing those sorts of shenanigans. But let's do that. So let's go over to Desmos. Here we are in Desmos land. And I'm going to make some of these things go away. They don't bother us as much. And we've got our two versions of our equation. We'll start with this version. And if I do that, I'm going to turn that one on. If we use that version, what we'll just have to say is when the function output, or y, equals 17.5, which is our version of 175,000 people. Okay, this is in the past, so it's before 2010. So this function is the one that uses x minus 2010. So x is the actual year that we're caring about. This function doesn't do that, so it's saying when x is 0, we mean 2010. So either one is going to give us the same kind of information. We just have to think about it a little differently. So if I use the equation that where x is the actual year, I can look at this and see that in 1957.9, so almost 1958, the population would have been what we wanted. On this one, 52, a little more than 52 years before 2010 would be when we had that population. So let's just do that. 2010 minus 52.007. And we get about that. And since I'm rounding here, we're just going to do that. Get rid of the 0.07, 007. And we get 1958 as the year, which is, in fact, pretty much what the year was. So about 1958, the population was 175,000. So we go back to here and we say in about 1958, the population was 175,000 people. And then we need to figure out the future one, and the future one is pretty straightforward. We're going to use 90,000, and in this case, I'm going to put the decimal here and make it y equals 9. And we go over here and we see where y equals 9, and 9 is representing 90,000 people. And this is y equals 9, and it intersects in our x is the year one at 2078, a little more than 2078. And this one, 68 years after 2010, which is about 2078. So there's some rounding to do. I'm just going to round it to the nearest year. In this case, I could round to the nearest tenth of the year, so 2078.3, so sometime in March or April of 2078. And I can just confirm that 2010 plus 68.3 is about 3/10 of the year. So we're sometime in late March, early April of 2078 for that one. And so we go in here and we say, yep, in about the year 2078, the town will have dropped down to 90,000 people based on all these assumptions. Clearly, things wibble and wobble, things change. The rates could be affected by new factors. But if we assume all of this is the same, the exponential rate is the same, we're good. I want to address one common mistake a lot of people seem to be making, which was folks were taking our original equation and they were adding 1 to this base. They were saying 1 plus da 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 da. And I think you were doing a little bit of a mashup of the situation where I've given you a percent. Here I haven't given you a percent. I've told you there's a percent, but I haven't given you a percent rate of growth or decay. So we're not adding our rate, our growth factor or decay factor, I should say, to 1 because the 1 is already embedded into this. This is going to be a 1 minus some percent. We could even figure out what that is. If we say this raised to the 1 over 7 power, well, we get this decay factor. And then if we say 1 minus that, then we get this rate of decay. This is actually going to be our rate. So it ends up being about a decay rate of 0.55% per year. So that's what this works out to. But that's the percent rate, and we're not needing that percent rate. I could have asked you for the percent rate, and this is how you would get it. We don't need it for this problem. We just need to know, what do I multiply our initial value by to get our later value? And that's this fraction. And then I need to break it up into 7 equal time z parts by using this denominator of 7 in the exponent. We're splitting this general base to get from 2010 to 2017 into 7 parts to get the yearly chunks, the yearly factors that we're multiplying by. Don't worry about the 1 plus, 1 minus if I haven't given you a percent. I hope this has been helpful. Feel free to email me with questions or comments.